In this lecture, we will be continuing talking about the kernel-based methods, and we will extend our so far discussion on sparse kernel machines concept. Kernel machines, we need to bring out a point about the main drawback of the kernel methods. Their computational efficiency is related to a calculation of the kernel and of the gram matrix and the possible inversion, and this needs to be done for all pairs of x and xm, so we are bound by the computational complexity with respect to the number of training points. And at some point, if we have a lot of training data, these approaches can become infeasible. And the main insight or gist about sparse kernel machines is that these sparse kernel machines are just picking few of the data points which are relevant for a given task, and they are taking those in order to formulate the solution to a given task instead of the entire training set. So these kernel-based methods have sparse solutions. We will be talking about two types of sparse kernel machines. One is the support vector machine, which is determining the model parameters as a convex optimization problem, and it's applied. It can be applied to regression. We will see it being applied on classification, and also it is used in novelty detection. This is a decision machine. This means that it's a decision function, and it doesn't really provide posterior probabilities like we have had the case in the case of, say, Gaussian processes, or we had it as an example of neural networks, or the some of the linear models for classification, which were probabilistic. And then, as an example of a probabilistic approach, we will be talking about the relevance vector machine, which is having a Bayesian formulation and provides posterior probabilities, and generally has a sparser solution than the support vector machine. So let's get started with discussing the concept of the support vector machine. We start with the classification task, which is a two-class classification using the linear models, where we will have a function y of x, where the x is a point in space, and this function y will essentially decide whether we are classifying it to one class or another class. So this is a linear combination of features weighted by the weights which we train normally in the linear models, plus a bias, which is here explicitly mentioned. Now we have a training set and associated input points and target outcomes. Here, the Tn is belongs to the either has a value or either -1 or 1. So not a 0 or 1, but -1 or 1, similarly to the perceptron, which we have been discussing before. And the data points are classified based on the sign of yx. So if the yx is equal to 0, we will be on the border of the decision boundary, and or at the decision boundary, and if we are having negative values, we are on one side. If we have positive values, we are on another side. Note that this is a line in the feature space. So yx would correspond to a line in the feature space, not in the original input space, but the feature space. Then, so we have for if the Tn is 1, the training data point, then the corresponding yxn has to be bigger than 0, and if the Tn is -1, the Yxn is smaller than 0, meaning that the product T and Yn is always bigger than 0 for all training data points. Now, for the example here, we are assuming that our data is linearly separable in feature space. So there is a solution to find a line in the feature space so that we can divide the points into the two classes according to the training data. But even if we have that, the solution is not really unique. We have several solutions here because we can put the line at a slightly different angle, slightly shifted towards one direction. It will be still defining the linear separation. So that is that would be not one solution, but many solutions exist. And for example, perceptron will find one solution in a finite number of steps, but the solution will depend on the W and the B initialization and the data point order as they are processed. So there are just picked one solution, but who guarantees that this is the best solution? It does satisfy the condition of linearly separating the training set, but in some sense it doesn't guarantee some best generalization. So ideally, from the multiple solutions, we should choose the one which has the smallest generalization error. So what does that even mean? Let's have a look at how such a generalization error can be conceptualized. So in the case of support vector machines, we define that the best solution is subject of a certain concept of a margin. So the margin is the smallest distance between the decision boundary and the samples. So you can see that here we have a margin. So we have here two classes, green and blue. They are linearly separable, and we can imagine that you can have separation like this or like this. Many separations exist. In fact, this entire interval of these parallel lines, it would be a separation, not including this line, but one which should be just below it. But now so this would be a valid classification result. However, it will be not the one which will have the best solution according to the support vector machines which utilize this margin concept. So the idea is that we will be the decision boundary finding by maximizing the margin. We want that this distance is maximalized. So therefore, what should be done? Well, maybe we can move this red line a little bit towards this direction, but then this another point will have this maybe margin smaller. So we need to this needs to be done in such a way that we find like a set of few points which will define us the largest possible margin. We cannot go further in this case because then we will be moving the decision boundary such that we will be making the margin smaller on one or the other side. So it's perfectly in the middle, maximizing the margin from more than just one point. So actually, the Bayesian approach for simple linearly separable data has also a decision boundary that is in the middle region separating the data points. So here we see somehow the correspondence to the probabilistic Bayesian approach. Now, let's have a look at how we can formalize this concept of a margin and how we can attempt to maximize it. I'm just taking an equation from our previous discussions on the classification, where we had this hyperplane generally in ND, but for the case of 2 dimensions, we would have only the line y of x will be equal to 0. That means that we have a function here which is equal to 0, and everything what is smaller than 0 will be one region, everything which is higher than 0 it will be another region. And on top of that, we can also evaluate, this is a value which is basically a real value, and then we can see how we can define this value y as the y at the point which is like closest point on the line with respect to the point x, and that is the point x perpendicular here, and its value is still y of this point is still 0 because it lies on the line. And then we have this distance is defined here as by this function y of x. That would be the function which is defining our value from this distance, and then we have this distance defined by r times w. So we don't know the r, which should be the distance, but we know the weight w, or the square of it. And it turns out that the distance is equal to yx divided by the w. So this is something which I am just repeating. We had it already on the classes related to the classification, and you can look it up. So now we can put into this distance definition that we are interested in points which are correctly classified. That means that we will have some positive quantity here if we multiply it by the training set Tn. So this is for the training set Tn, and this is the distance for each of the training point. And here we can see that we have expanded the formulation of the y by this linear model, where the weights are multiplied with the feature vector plus the bias. So this will define us the distance, and for each of the point, and one distance will be smallest distance, and this will define some closest point xn, and this closest point xn will define the actual quantity of the margin which we want to maximize. So the goal is to optimize the w and b to maximize the distance to the closest point. Here we can see it formulated in the formal way, where we pick the minimal n, so for which the distance is the smallest, and we do not really need to divide it by the w here, because that doesn't depend on the particular value n. That's the same for all values, but this distance now will be for some value it will be the smallest, and we will pick the minimal n therefore. And given the minimal n, we will be making this distance calculation to be as big as possible, maximizing it by optimizing the w and p. So this would be a complicated optimization procedure. Therefore, we will be defining a simple way how this can be achieved. So first, we can note that if we rescale the W by the kappa W and B by the kappa B, the distance does not really change because we are having the W in the numerator and square in the denominator, and it will always be normalized by this square of the weights. So if we are decreasing the weights uniformly or increasing them, that will have no impact on the value of the distance. So we can therefore set the distance to the closest point so that the value of Tn W phi x n plus b, so the numerator part of the distance, will be equal to 1. So we can set the W such that this property will be fulfilled, and therefore we will have this as this is for the closest point. So basically the margin will be 1, and the canonical representation of the hyperplane where all data points satisfy this condition is this is the canonical representation. So this is the where we have the y and the multiplied by the Tn, and it's bigger or equal to 1, meaning that the closest point is equal to 1 and all other points are bigger than 1. So, and then we can define for points to be either forming an active or an inactive constraint. And an active constraint is only for the points for which this equality holds. So normally, maybe it would be just for one point that is the closest one. Once we are performing the optimization, the number of points for which this optimization is forming as the active constraint, at the end of this optimization, we will have at least 2 of such active constraints, because there will be at least 2 points defining this margin from to which the margin or the distance will be exactly the same to each of these 2 points on the either side of the decision boundary. So therefore we want to as we want to maximize the distance, we want to maximize this this weight here, and so we want to maximize 1 divided by the weights, and weights length, and that can be reformulated to minimizing the so we maximize the reciprocal of the length, and here we are minimizing the square length. So the idea is that we want to have an optimization which is minimizing the square length of the vector W, and this is a typical quadratic programming problem where we are minimizing the quadratic function under a set of linear equality constraints. So we can do it in the following way. So the convex optimization problem will be expressing the optimization of our weights, which we want to their squared length we want to minimize of the weight vector, but at the same time it's constrained by the constraints, which are expressed through this in this Lagrangian formulation using these Lagrangian multipliers, which are an or alpha n in other sources, which are, or lambda for that matter, which are bigger than 0, and for each training data point. So we will have a vector of A, and we would be actually maximizing this this vector A, for which we will be then also maximizing the distance, as we will see. So we can formulate the Lagrangian formula where we have the weights, the bias, and the Lagrangian multipliers, and here we see simply this that we have the we want to optimize for having as small weights, so this is a minimization, small weights as possible. So by observing this square of this weights vector, and then we want to so this is we minimize, and we want to maximize this term here, which is the maximization of this distance, and we have a constraint that the distance has to be bigger than bigger equal than 1, so that's why here is the -1, and here we have this Lagrange multiplier, and we do this for all training points. Now we can also reformulate this slightly by this term stays the same, and then this overall sum can be seen that we can multiply this an by the -1, and therefore we will have, instead of here minus sum, we will have a plus an here, and then we will have two more sums. One is associated with the tn an times tn and this term, and another one is associated with the b. So we have these two terms here as well, and now we are performing the the minimization of the w while maximizing the a, and that is through here we set this the derivative of the Lagrangian equation to 0 with respect to the weights, and that will lead to the fact that we just perform the derivative of the weights here. Therefore, this term will change to a 2 times the w, so that means that we will have the vector w here, so the 2 will be cancelled out, and then we have also this term will go away, this term will also go away, and here we will have one term, or where, because we have the weight here, so we will have finally, so this is minus here, this is plus, so therefore this partial derivative with respect to the w implies that the weight will be calculated as the sum of this the constraint Lagrange multiplier and the feature vector for the xn and the tn, whether it's a positive or negative, and that will define as the weights. And we also will be performing the partial derivative with respect to the bias, and that should be also equal to 0. And if we perform that, we will only have this term, which is a negative here, to remain, and that will lead to the formula that an times tn is equal to 0. So these two formulas will, so this one will give us somehow a constraint, this one will give us a way how we can calculate the weights out of this formula in principle, or how can we replace the weights by these terms. So if we are doing that, we can replace the weights into this formulation, and we can see that this weight squared can be replaced by, so as it is a squared, it will be, this is a sum, so it will be a double sum and a product of different Lagrange multipliers, different target values, and the phi's, where the phi is will be now a multiplication of, so I mean the phi's, which is now formulated as a kernel, where the kernel function is a dot product of two feature vectors. And then we will have this term, which is unchanged here from the original formulation, and then we have this term here, where the weight W is again replaced by this formulation, and it has this form, which is very similar to this form, besides the fact that this is now a 1/2, and here we have the 1 or -1 multiplier of the same term, which will effectively lead to the fact that our resulting formula will be an sum minus the 1/2 of this term, and we are trying to maximize this this Lagrange multiplier to find the maximal vector A. Now, one thing is that this term also has been removed, because we have realized that an times Tn is equal to 0. Therefore, this term is no longer in the formulation. Once we train our support vector machine, we can classify the new points x by the formula as we had it before, the y of x, which is the formulation with the weights, but we have now already have derived out the weights, and we can replace it by the formulation which is weight free, and we have only the formulation based on the optimized an vector, which was maximized, and then we have the Tn, and then we have the kernel. That's why this is a support vector machine, is a kernel method. Then we have also here plus b. We will soon see how we can calculate the bias, which has not been taken care of explicitly yet. And we see that this solution will satisfy the so-called KKT or Karush-Kuhn-Tucker constraints, where both in general that constraint means that the lambda and also some function gx, which we are trying to maximize, is equal to, is bigger than 0. So the lambda is bigger than 0, and the gx function is also bigger than 0, and then that the product of these two is actually equal to 0. So equal here is bigger and equal to 0, sorry. And if we translate it to our case with our naming scheme, we can say that our an components of the A vector should be all bigger than 0 or equal, and then the distance should be bigger than 1. So the distance before the normalization by the squared weights, and then this also means that for some of the points, this actually should be equal to 0. So this way, this distance should be exactly 1, and this an will basically give us values where we have an will be 1 when we will have we will be on the support, which will be forming the points which are defining the margin, and for all the other points which are behind the more far away, so to say, from the decision boundary, the AN will be 0. That will create this sparsity that only few points will be considered. So if AN is 0, then that training point will not appear in the sum for the prediction of the new points, and if the AN is equal to 1, then these are the remaining points which are called the support vectors, for which the Tn Yn is equal to 1, so that they will be forming this margin, and there will be at least two support vectors lie on the maximum margin hyperplane in the feature space. So on the line as the maximum margin line in the 2D, as we have seen. And once the model is trained, therefore, we can discard most of the training data points and only use those points which are forming the support vectors, which are kind of holding this decision boundary and these maximal margins. Our optimization approach will, in the dual form, will maximize the AN, and finally, once the optimization concludes and the vector of AN entries is identified, then we can proceed with, for example, calculation of the weights. As we see that the y is equal to the weights times the feature vector plus the bias, we can stay with this formulation, and we can calculate the weights from this formula, which we have devised before, because we have identified this formula by setting the derivative with respect to w to 0. Now, however, in case of the support vector machines, many of these ANs will be equal to 0, because these points are not really on the close to the boundary of these two classes, and therefore the AN will be 0, and only the support vectors will have the value 1. Therefore, we can also have a much simpler calculation of the W, where we only include the points which are in the set of support vectors, and then we only perform the multiplication and the sum of those, because those will be actually contributing to the value of the vector W. However, we can also entirely skip the calculation of the W's and use the kernel instead for calculating the values Y. But even if we do that, we would need to calculate the bias, which we still haven't calculated yet. So how can we approach the calculation of the bias? We can see that for any of the support vector, the following formula holds. Tn times yxn is equal to 1. That was the definition for a support vector. And here we can formulate that the yn or yxn is equal to the parametric formulation here with the weights. However, we replace these weights by our vector A entries as according to this definition. And we can see that this term in the bracket can be represented by the sum of the across the all support vectors, and multiplied this term, which is the weight, times the phi, and we can even put the phi xn here, so that's for any support vector, which is also part of this set, by the way, of m's. This support vector is multiplied in the bracket with each of the entry of xm. So, and then after we perform this this sum, we can add the bias term. So this is just we start with the definition of any point which is the support vector. It's this whole formula holds Tn yxn is equal to 1. Then we replace the yxn by its formulation of using the weights, and then we use the formulation of weights in order to formulate it with this dot product of features and with the vector A, which we have optimized and acquired those values given the optimization process, which was constrained by the constraint we talked about on the previous slides. So having this, we end up with this formula where this is equal to 1. And we can also say that the Tn squared, no matter whether the Tn is equal to -1 or 1, as the classification of these two classes, it will definitely, its squared will be equal to 1. So we can put that the Tn times this equals to Tn squared, and then we can get rid of one of the Tn's on each side, and we end up in the formula where this sum plus b is equal to Tn. And then from that we can express the b, where the b is equal to Tn minus the sum where we are using this the sum over all support vectors, and the one of the support vectors is chosen as the Tn here, and here we are using already the formulation of the kernel, which is coming from these formulations of the dot product of the feature vectors. Now that can be one way how we can formulate it. Another way, which is considered to be more numerically stable, is that we do it for all the support vectors here, and therefore we perform this Tn minus this sum here, which was once calculation of b. We perform it n times over all support vectors, and divide by the number of support vectors. So we basically create a B which is an average of all the B's mentioned or identified in this by this formula. So that is how we calculate the B, and once we have the B, we can put it into the kernel formulation or the weights formulation for calculating the support vector machines. Please note that we can also express the maximum margin classifier, like the support vector machine, as a minimization of the following error function. So here is a relationship to error functions which we were dealing before with, and here the error function is the E infinity of the argument, which is our the distance or the numerator of the distance, which was yx and Tn minus 1. This term will be equal to 0 for all the, so this error will be equal to 0 for all the z's which are bigger or equal to 0. And otherwise it will be infinity. This means that the error for all the points which are more far away from the decision boundary, then that will be this will result into a value which is, this will be a higher value and than 1, and therefore we will have here a 0 error. And otherwise, if we will be close to the decision boundary, then where this term is smaller than 1, in such a case, we will have an infinitely large error. And then we have the second term here, which is represented with this regularizer lambda, where we can see that we are attempting to minimize the weights, the weight vector. So that could be a formulation of how we can formulate the maximum margin classifier as a minimization of an error function. We will be seeing in the next how we perform this, the optimization using quadratic programming. But for now, we can already see that if once we calculate the A's and the B, then we can already calculate what will be the classification of our points. And that we can see already here as the result of the support vector machines. We can see that this is in fact we see that this is a picture from the input space, where we have the classification of points X, which are in one class. Red X's are one class, blue X's are another class, and we can see that they are not really linearly separable. So we cannot really find a single line which would be linearly separating these two classes in the input space. However, we have the feature space, and here actually the kernel is a Gaussian kernel, which as we know, has this corresponds to an infinitely dimensional feature vector. And we can see that in this, using the Gaussian kernel in the feature space, there is a possibility to find a boundary. So it is linearly separable in the feature space. We don't see the feature space here on this plot. We see only these curves here would be lines in the feature space. And therefore, we can see how this feature space is somehow deformed with respect to the input space. Now, we can see that there is a decision boundary, which is this thick line, and we can also see what are the various points, like these blue points in the green circle are the support vectors on one side of the decision boundary, and then we have the other support vectors on the other side of the decision boundary, which are defining us this this margin, which is then equal on each side after the optimization is completed. In many cases, we have situations where the classes are in fact overlapping, meaning that we have several points which might make it impossible to make our classification linearly separable problem in the feature space. So in such a case, we cannot really impose a hard margin constraint, because there would be no margin to define in such a case. And therefore, we instead will reformulate the hard margin support vector machines case into something which can be referred to a soft margin, and that will that technique or approach will allow misclassification. However, it will be penalized, and it will be penalized with a penalizing term that will be basically proportional to the distance from the decision boundary. So it will be a linear function of the distance. And for this purpose, we will introduce new slack variables, xn, which will be bigger or equal to 0 for each data point. So in addition to what we currently have the point input point xn, its classification tn, and we have seen that in the support vector machine optimization approach, we have been optimizing the an entries of the vector A. Now we will have a vector xi which will have additional entries necessary for defining the slack variable, which will encode whether our point is within the margin or whether it is sort of behind the margin of the decision boundary, or whether it is within the margin on the correct side, or whether it is in fact a misclassified point. So we will define that for all the points which are inside or on the correct margin boundary, meaning for all these points here in green or these in the cyan, they are, when this is the margin, they are behind the margin or on the margin, and for those points we will have the slack variable cn equal to 0. And for the all others, which are either within the margin on the correct side or actually misclassified, as for example this point here, then we will have the cn encoded by tn minus yxn. And the yxn will be for our line. If the point is on the line, it will be this term will be 0, and therefore we will have the cn equal to 1. So we can see that the cn is within the range 0 to 1 if it's within the margin on the correct side of the decision boundary, and if it's misclassified, is bigger than 1. So for a point on the decision boundary, right the line, the cn will be 1. Otherwise, if it's misclassified, the cn will be bigger than 1. And our classification constraint, which was previously that y, x, and tn should be equal to 1, we are extending it to y, x, and tn is equal to 1 minus cn. So if the cn is equal to 0, then we will have the original formulation, and if it's bigger than 0, so maybe smaller than 1, then it will be positive, and if it's misclassified, this outcome will be in fact negative. So it is consistent that a negative outcome means a misclassified point. Therefore, our goal will be to again still maximize the margin with softly penalizing the points on the wrong side of the margin boundary. So we will have here, we want to minimize the distance, which we found out previously that this is the that's how we want to minimize this term by changing or optimizing the W and the bias. And we want, now we have an additional term where we want to minimize this Cn, and we have here some constant C, which acts as a regularizer or an inverse of a regularizer, which will be defining us how much of the penalization, soft penalization, do we allow. So if the value is very small, we allow a lot of penalization. If because this term will be already quite small, if it is very large, this C, this error will be very high, it will be scaled with that. So in the case that C is infinity, we will resort back to the hard constraint case. So, and it basically is defining as the upper bound for the number of the misclassified points, which is in by the sum of this slack variable. It is an upper bound because if we are just on the decision boundary, this slack variable will be equal to 1, and if it is behind the boundary and more far away, then it will be increasing with the distance. So if all points will be misclassified, meaning that they are just on the decision boundary, then not all points, but the points which have the non-zero Xn, that will mean that we have this number of misclassified points, because each of them will be equal to 1. However, in our case, we have the Xn is typically bigger than 1 if it's misclassified. That means that the Xn, so this sum is characterizing as an upper bound for the number of misclassified points. As we said, the parameter C controls the trade-off between the slack variable penalty and the margin, and acts as a reciprocal of the regularizer. So the hard margin can be of support vector machine can be recovered or reformulated if the C is goes to infinity. And in our case now, with this soft margin, we are having additional terms in our Lagrangian formula. So we would have the minimizing the distance by this term. Then we have our other term, which is characterizing the maximal number or upper bound of number of misclassified points here, which is controlled by the C, and then we have our sum, which is characterizing as the formula of the distance or the classification, which is should be bigger or equal to 1 minus psi n. So this is the constraint, and then we have another constraint which is characterizing as the these slack variables, where we have the mu is another Lagrangian term. So mu n and an are both Lagrangian terms. The an has the similar or the same role as before, and we have the following conditions to fulfill: is that all the components of the A vector and the mu vector Lagrangian should be equal or bigger than 0, and that our slack variable is also non-negative for all its components. Then we have the other constraint that this Tn minus y, Tn y xn minus 1 plus psi n is bigger than 0. And finally, we have that, so that is our this gx in these KKT conditions, and then we have the constraint that either an is 0 or this value is 0 for non-zero a, so that this term is always equal to 0, and also that the product of Cn and the mu n is equal to 0. So for all the points which are having the Cn 0, the mu n can be 0 or non-zero, but for all those which are non-zero, the mu n will be 0. similarly to our hard margin case, we will be performing now the primal dual optimization. So first we are performing an optimization with respect to the W and the B and the slack variables. And we can see that if we set this partial derivative of the Lagrangian formula with respect to weight to 0, that will lead to the same outcome, that the sum of our AN, TN, phi, xn is equal to the weights, because from the derivative only the weight squared and this term were containing weights, and then when we set the partial derivative of the Lagrangian with respect to the p to 0, then again we will, this implies that the sum of a and tn should be equal to 0. And then we have which somehow characterizes the fact of symmetricity, that in some these ANs which are non-zero should be multiplied by either +1 or -1, and they should in sum be finally equal to 0, so that this this margin is of the same distance from both classes. And here we have a new partial derivative of the Lagrangian formula with respect to the slack variable, and that is equal to if we set that to 0, then this slack variable we have in several terms in our Lagrangian. So you might remember from the previous slide, it is the c times the sum of the slack variable. So therefore we will have the c here, and then there is the slack variable is also associated with a negative or sum of an multiplied by tn yxn minus 1 plus the xn. So in that case, the a minus an will be part of that those terms which are remaining after the derivative, and then there is the sum mu and Cn, where the mu minus mu will be part of it. So if we put the an on the other side where there was previously 0, so an is equal to c minus mu n. And that means that if so, we know that this term needs to be 0 or positive, therefore an needs to be either something between 0 and c. And this is how we are somehow constraining the values of an through this soft margin parameter c. And we are talking about the so-called box constraints of the dual variables an. Now, if we are performing the reformulating the Lagrangian formula with after we acquire from the primal variables and their derivatives the respective relationships, we will find out that we end up in the same formula as before, where we have the sum of an minus half of the double sum, where we have both the a, m, and the t, both t and the kernel components. And this is our Lagrangian formula, which we are trying to maximize. And we are maximizing it by finding the appropriate vector an, which will be maximizing this formula. Once we find that by means of the optimization, like in this case quadratic programming, we will then be able to classify the new points by this formula, where we do not even have the weights here, because the weights have been now represented by these terms, where the kernel xn is also representing the dot product of the feature vectors. So it's no longer the weight representation necessary. Similarly to the hard margin case. Let's have a look at the characterization of what does the various values of an or the other parameters indicate. So after the optimization, all the points which have an is equals to 0 are points which are not considered as the support vectors and are safely far away from the decision boundary. Then we have support vectors for which the an is bigger than 0. And for those, we have the following formula needs to be satisfied, which characterizes as the value, for example, of the slack variable. Then if the support vector an has an associated variable an which is smaller than c, after the optimization is converged, then that means that our mu n is bigger than 0, because we have the formula that the an is equal c minus mu, and if this is smaller than c, then mu has to be non-zero, so it has to be bigger than 0. Then we have another constraint that the mu n and the slack variable together as a product needs to be 0. So if this part of the product is non-zero, the slack variable needs to be 0, meaning that we are a support vector which lies on the margin, and therefore we have the slack variable which is somehow expressing the error of or degree of error of classification is 0. For those points which after the optimization, their an is actually equal to c, so then those points lie in the margin, either correctly classified, so but within the they are in that margin, not very close to the decision boundary, and their cn is between 0 and 1, or they are even misclassified, and then their cn is bigger than 1. For the calculation of our classifier, we still need to find out the parameter b, and this parameter can be defined in the same way as we had it before, where we have the these two this term with the tn minus this sum as we defined it before, and we can average it through the several support vectors. So the set S are the support vectors, and we simply calculate the b from the tn minus this sum, and if we want to have a numerically stable solution, then we calculate it for each support vector, which for each tn here, and then divide by the number of support vectors, and that will give us the b parameter. As an alternative to the soft margin SVMs, we have the new SVMs, which are an alternative and equivalent formulation. This is just to understand that there are many variants, and one of the variants is that the Lagrangian is formulated as a only with this part, so it doesn't have the sum of an first component, and then the an is constrained to be within 0 and 1 divided by n. And then also there is another constraint, which is bringing in this new parameter, and the new parameter is telling us that the sum of ANs is bigger or equal to the new. That means that the new is replacing us the C in this soft margin case, and can be interpreted as a lower bound of Vn being the fraction of support vectors. So meaning that if we have here the new certain value, then if in case we will have ANs having the maximal value, meaning the 1 divided by n, then here the value which, so that we can satisfy this condition, an is 1 divided by n, then 1 divided by n and times is times the new will be having the new equal is bigger smaller new. So that's why this is the lower bound of the support vectors. This characterizes the lower bound of support vectors, but there could be even a larger number of soft vectors, support vectors, but at least the new times the n support vectors will be forming our margin and decision boundary. And then it can also be seen as the upper bound of the margin errors. So because if we have the margin errors are only if all of the ANs will have the value 1 divided by n, that means that they are behind the margin or even misclassified, I mean behind closer to the decision boundary or even misclassified, they would have to be equal to the 1 divided by n. And if that's so, then there will be new times n of such cases where we will have indeed a margin error. But if they are smaller between the 0 and 1, then new n will be equal to 0. So only in case if all ANs are equal to 1 divided by n, then or the new n cases of AN is equal to 1 divided by n, in such a case the this value will be bigger than 0, so therefore it is the upper bound. Finally, we have here the an example of this soft margin variant new SVM, which is characterized by the kernel of the exponential function here, or a Gaussian kernel with the parameter gamma is equal to 0.45, and we can see that here is we have a lot of the classes are overlapping, and despite that there is a decision boundary shown here for us, and we can see how many of the points in fact are support vectors. So that depends on our setting new, which defines us then the margin and the corresponding support vector, which points are the support vectors. After we became more familiar with the concept of support vector machines, both the hard margin and soft margin concepts, we will have an exercise of this classification approach on a trivial example, in which we will also see how this quadratic programming leads to the optimization outcome. So we have a test case where, we have the training set where the x1 point is 0, 0, and it is classified with the t1, which is +1, x2 is 1, 0, and that is the t2 is still +1. Then we have point x3, which is 2, 0, and the t3 is -1. So trivially, we can see here that 2 points are on one side and 1 point is on another side of the decision boundary. Now, we could even, by just eyeballing, say that for us, the most natural way of putting the decision boundary will be in the middle between the point x2 and x3, and at point 1.5, that should be the decision boundary, and that is relatively simple to just find out without any calculation. So here we will see the systematic way how we obtain a result which is somewhat similar to what our intuition is saying. We will have to deal with a case with a soft margin, also because our distance, the margin, cannot be here of a length or distance 1, and therefore this hard margin case cannot be satisfied, and we will therefore resort to the soft margin, and we will define that our C is some value which we set as fifth, eighth as a threshold parameter. Now, in the primal form, we will be minimizing the Lagrangian formula, which is consisting of the several parameters, and we will differentiate with respect to these parameters, and we will come to the conclusion that our final result with respect to our dual form will be that our dual form has the formula as we are used to from the SVM definition. So this is the sum over an minus, and then we have this case here where we have the double sum an, t, and tm, and then we have the kernel, which is here in this case a linear kernel. So our input space is our feature space, and we have various constraints here, like for example that the an is bigger than 0, and then a1 t1 plus a2 t2 plus a3 t3 is equal to 0. So this was a constraint which was coming from the partial derivative with respect to the threshold parameter b. So after we have our Lagrangian formula, we can prepare some of the values which we need to use for our calculation. Like for example, we will fill the gram matrix with our entries. So with our dot product x1 with x1, x1 with x2, x1 with x3. This all, as x1 is 0, 0, will lead to 0. So because we want to have a very simple case, and then x2 dot product with itself is equal to 1, because here we see that this is leading to 1. Then we have x3 transpose x3 is equal to 4, and x3 is equal to 2. So we can see that the gram matrix is forming us this form here, and then we have the t2 squared equals to t3 squared, and that is equal to 1. Because we need this in our formulation, we do not need t1 really, because every time there is a t1, this will be by this dot product will be whole term will be 0. So we only need to find out what is t2 or t3, and t23 is equal to -1, because 1 is -1 and 1 is +1. So now we have pre-computed several of these values, and we can see if we now plug in our terms, what are they what will be the corresponding to. So here we can see that we can now go through all our values, like m equals 1 to 3, n equals 1 to 3, and we will find out that the outcome of this term here, which is then 1/2 of it in our Lagrangian formula, is a2 squared minus 4a2a3 plus 4a3 squared. Why is that? Well, simply if m is 1 and n is 1, or n is 1, we will have here 0. So m is either 2 or 3, n is either 2 or 3. So if m is 2, then we have the term here is 2 times, and now let's say the n is also 2, so then we will have here the a2 times a2, and in such a case, if n is 2 and m is 2, then this is then t2 times t2, so this is t2 squared, this is 1, so this is a2 squared, and times the dot product here, which is 1, so that gives us the a2 squared term. Now let's say the m is still 2, but n is 3, or otherwise, but let's say m is 2, n is 3, so this is 3a3 times a2, and then here we have t3, t2, so a3, a2 times minus 1 because of this term here, and then times the 3, 2, so that's like a 2, 3, that's 2. So we have minus 2 a2, a3, and if we have here 3 and here 2, the same will be the outcome. So we have actually twice that term, and therefore we have here minus 4 a2, a3. And then when both n and m are equal to 3, then in such a case here is a3 times 1 and times the x3 transpose x 3 is equal to 4, so we have the term 4a3 squared. So this is the outcome of this term, and then we have this term here, which is calculated as a1 plus a2 plus a3, and that will give us the Lagrangian formula. Then we have also our constraints, which say that a1 plus a1 or both a1, a2, or a3 have to be bigger than 0 or equal to 0, cannot be negative. And we can also see that a1 plus a2, they are like we have here this constraint, the following constraint: t1 is 1, t2 is 1, t3 is minus 1. So we have that this needs to be equal to 0. So a1 plus a2 minus a3 equals to 0. That means that our a1 is simply a3 minus a2. And that also leads to the fact that the a3 needs to be bigger or equal to a2, because otherwise, if this will not be the case, a1 will be negative, and a1 cannot be negative. Therefore, a3 needs to be bigger or equal to a2. So that's another constraint. Now, we can express the a1 by this formula, a3 minus a2, and put it into our overall formula here. We will find out that this term here, a1, will be replaced by a3 minus a2, and that will mean that we will have here a3 minus A2, so the A2 will be here removed, and instead of 1A3 we will have 2A3. So finally our Lagrange formula will be equal to A2, we'll have only A2 and A3 components, and the formula will be 2A3 minus, and this in this formula here which have been acquired from this double sum. So we have our Lagrangian formula, and now we will be maximizing it. So once again, here is the formula, and we will be performing the maximization. Now first we perform the derivatives with respect to A2 of this formula and A3. So with respect to A2, the formula is as follows. We can see with respect to A2, this is a constant, is removed, and in this bracket we will have 2A2, which is here, and then we have here 1A2, so minus 4A3. So this is the partial derivative of the Lagrangian formula with respect to the A2. So the result is, we can see 2A3 minus A2 once we are performing the trivial reformulation. The other case here is that we have the partial derivative of the loss with respect to A3, not loss, Lagrangian formula with respect to A3, and we are now so this will be 2 after the derivative, and here this is a constant, so it's 0, and then here we will have 4A2, and here we will have plus 8A3. So this times minus 1/2, we will end up in a formula that this Lagrangian partial derivative with respect to A3 is 2 plus 2A minus 4A3. And we will start initialize our values of A1, A2, A3 with 0. So that's the 0th iteration. And we will perform with these values now the partial derivative. And the partial derivative with respect to these zeros for A2 and A3 with respect to A2 will be equal to 0. Because if we put here zeros, then the result will be 0. In this case, however, we will have the outcome will be 2, because this is the formula, and even if these 2 will be 0, we will still have this 2. That means that we can increase the A3 from its value 0. The question is, how much can we increase it? And the answer to that can be defined by this integral of the partial derivative, where we define A2 as a fixed value 0, and then so when we put the 0 for A2 here, we will have the formula 2 minus 4A3 is equal to 0, because we are trying to maximize this partial derivative, or this Lagrangian formula with this fixed 0, and then that will lead to the fact that A3 after first iteration is equal to 1/2. And as A2 is equal to 0, then A1 is equal to 1/2, and it is positive, this is positive, A2 is 0, so that's also fine. So in fact, all the constraints are satisfied, and they are also smaller than 5/8, which they should be the C, which we have defined in the beginning, was defining as the maximal value of the parameters components of the vector A. So 5/8 is bigger than 1/2. And then in the second iteration, we will now see if we put for the value A3 1/2, and for the A2 is 0, what is the partial derivative? And here we can see 1/2 times 2 is 1. So this is 1, it's positive value. That means that we can increase the A2, and the question is by how much, and then we can maximize the Lagrangian if we fixate the A3, and the partial derivative of the Lagrangian with respect to A2 will lead to the 1 minus A2. So 1 minus A2 is equal to 0. Therefore, the A2 will be 1. However, A2 cannot be bigger than A3, and therefore we will crop it to the value of 1/2, because that's the maximum value it can have, so that it doesn't break any of the rules. A1 stays positive or non-negative, and all the A's are smaller than the fifth, 5/8. In this case, we will have a look in the third iteration. What is the partial derivative with respect to A3 if we have the values 1/2, 1/2 now for both A2 and A3? And that is equal to 1. So we can see here 2 plus 1/2, 2 plus 1 is here 1, so that's 3, and then 4 times 1/2, or minus 4 times 1/2 is 2, 3 minus 2 is 1, so we can still increase the A3. And then we perform the partial derivative here. 2 plus 1 minus 4A3 is equal to 0, which means that A3 is 3/4, and that cannot be, because the C, we can be as much as the C. The C is now 5/8, so therefore the A3 can reach the value 5/8. In such a case, as our A2 is 1/2, the A1 will have the value 1/8. Now still with this, all the constraints are fulfilled, and we go to the next step, where we have our values for A2 1/2 and for A3 5/8, and we perform the derivative with respect to A2, and we see that it's positive. So when we put here 1/2, this is 1 minus 5/8, we will still be positive, having a positive value, and that will lead to the partial derivative with respect to A2 when we put 5/8 for the A3, and that is now therefore 10/8 here, and then we have minus A2, therefore the A2 will be equal to 5/4, but it cannot be that large. Maximally it can be 5/8, and that is the value which it will obtain. Therefore the A1 in the fourth iteration will become 0. So the outcome of our quadratic programming is leading us to the final value of the A vector, which will be 0, 5, 8, and 5/8. So that is the outcome of this optimization approach, and we can, once we've completed this optimization, we can proceed to the next stage, so that we can define the classification. So we have now here again this function. We can see just by how, when we were changing these values, that indeed our values were changing also for the Lagrangian formula, and we were indeed making it bigger and bigger and maximizing it. So we can see that for 0, 0, this formula will become 0. For 0, 1/2, we have here 1/2 will be here, therefore 1, and then here we have A3 squared, which is equal to 1/4 times 4 is 1 minus 1/2, so it times minus 1/2 will be 1/2, and A2 will cause these two terms being 0, and therefore 1 minus 1/2 is equal to 1/2. For the second iteration, both of these are 1/2, and therefore we will have here a slightly more complicated formula where we have again 1 and then other values we are just putting in. I will not go through it in very detail, but we can see that we are ending up with the value which is 7, 8, which is bigger than the previous value. So we are clearly increasing the value of this Lagrangian formula with our parameters through the optimization process. And then we have the L3, where the third iteration, where we have changed the A3 to 5, 8, and we can see that the value has changed, and we are almost, so this is close to 1, but this is even closer to 1, 62 divided by 64. And finally, in the fourth iteration, where both are 5 eighths, we can see that the value is even increasing, and it's slightly above the value 1. So, and at this point, the optimization stops. This is the highest value the Lagrangian formula can obtain. And we can also see that we are in the case that both of these so A1 is having the value 0, A2 is equal to C, and A3 is equal to C. So, which means that both of them are in fact within the margin, and therefore they are causing us a non-zero xi error term, which is the xi's are non-zero for these two points. So we can see that we have for A1 is so if an is equal to 0, then the tny xn is bigger than 1, and then for those which are between 0 and c, then we have this is then equal 1, and then for those support vectors which are in the open interval 0, c, so that's the equal, and for those which are equal to c, we see that the tn y xn is smaller than 1, and because we have here this value of nu, which is the characterized, this like variable, which is characterizing as somehow the error. So we can calculate out of, we could calculate out of these values am, which we have obtained, and all the other values, the b. However, we encounter an interesting problem. Our set of the support vectors, which are between 0 and c, an open interval, is empty set. So we do not, in fact, have any such support vectors which will be directly on the margin. They are behind the margin, close to the decision boundary, both of them, and the one which is at the 0, 0 is not a support vector point. Therefore, we will see how we can alternatively define the B in this framework. So as T1 yx1 is equal to, so T1 is plus 1, therefore yx1 is bigger than 1, and for the T2 yx2, for the T2 is also T2 is also 1. However, we can see that we have this formula here. So yx2 is in fact smaller, equal 1. And for T3, this is minus 1. And that will lead to the fact that minus yx3 is also smaller equal 1. And now we have the following formula for our yx here, where the b is present, and we can, for each of our 3 points, we can express what the b needs to be, so that this formula is satisfied correctly. So for yx1, we see that this will be 0 here, and therefore we have, sorry, this term will be always, this kernel will always lead to 0, because the x in our case, if this is x1, which is 0, 0, this dot product will lead to 0, so this entire sum is 0, and therefore the yx1 is equal to b, and that leads to the fact that the yx1 needs to be bigger than 1, and therefore b needs to be bigger than 1, bigger and equal 1. So, and then for the second case, for the second point, we see that we have the formula here, or we reformulate this so that we can easier see the values. So it's a2 star, meaning the 5, 8, and then we have +1 here for associated with the a2, and then we have the kernel of x2, which is equal to 1, and then we have the a3 star, which is 5, 8 minus 1, so that's the t3, and then we have the kernel x2, so, and that is equal to 2. So therefore we will see that that leads to the fact that yx2 is equal to minus 5, 8 plus b. And as yx2 is smaller equal 1, that leads to the fact that this term needs to be smaller equal 1, and we will come up with an outcome which says that b needs to be smaller equal 13/8. So it needs to be bigger than 1 and smaller than 13/8. And then finally here we have the formula for the x3, and the formula for x3 will tell us that the yx3 is equal to minus 10/8 plus b, and that leads to a value of the yx3 as it needs to be small, minus yx3, which needs to be smaller than 1. Therefore we have here minus 10/8 plus b is smaller than equal 1, and therefore the b needs to be smaller equal 13/8, and that in fact leads to the outcome that b needs to be not 13/8, sorry, 10/8, that the b needs to be bigger than 1/4, and that gives us the conditions: b needs to be bigger than 1/4, b needs to be smaller than 13/8, and b needs to be bigger than 1. So the interval on which b is valid is between 1 and 13/8, and we can in fact pick any b for our classifier. So we will pick, for example, 1, because this is very easy to handle. So now, as we just said, this is the b is valid on this interval. We pick the b is equal to 1. And now, just to see how our overall support vector machine with the soft margin works, we can just put in several points. All of them are on the y equals, or x2 equals 0, and therefore we will be just dealing with one component of this vector in these otherwise 2 dimensions. So we have here our formula for classifier a y of x. If it is positive, then we are in one class. If it is negative, we are in the other class. And we can see here that we have here the b, so we have already expressed the b, and we can therefore define ourselves the formula for all of these points. So the n, there are 3 points, so n goes from 1 to 3, and for the first point this n is 0, so therefore this point will be cancelled out anyways. And then for the other points, we have for the n equals 2, a2 is 5/8 times 1 times and the kernel, which is the dot product between one of our x values, the points which we will be testing with, and the xn will be the is in fact 1, because it's the x1 component of this vector. So this is not a vector, this is a component of the vector x2, and this component is equal to it's equal to 1. So multiplied by 1, it's just x1. So of the first component of this vector is here. And then for this, the second term, we have the n equals, small n equals 3. So this a3 times 5/8. And then we have this term here, which is -1, therefore minus here. And then this kernel computation will lead here to the 2, because the component, the first component of the x3 is 2, and we will be multiplying it with the x1, the first component of this vector. And finally, the b, we have defined that it's 1, so we have here the final formula. Actually, we can still reformulate it, and therefore, as here is 2, we will have 1 minus 5/8 x1. So if we put in here for the point 1 to 0, then we will have here 1 minus 6/8, which is 4/8, which is positive, which means that our point will be classified on the as one of the points on the left of the boundary. For 1.5, which we said originally that there should be our decision boundary, we see that our classifier is almost at 0, but it's not completely 0. And that is also thanks to the value which we have decided for the b. And then we have the last point, which is the 2 more points, 1.6 is, and we see that for 1.6 we have here actually 0. So the decision boundary is a line which goes across the point 1.6, x equals to 1.6, or x1 equals to 1.6. And then for 1.8 we see that the value is already negative, so we are in the another class. And with this, we have seen how our classification outcome, what does it results to. We have been utilizing this soft margin case of this classification. And on this trivial example, we have seen all the steps which are necessary to be performed in order to perform this or train this this decision machine of soft margin support vector machines. While support vector machines have been primarily understood and utilized in the context of two-class classification, we can reformulate the concept of support vector machines also for the regression task. So let's start with our quadratic error function, which we have been utilizing in our regression tasks before, for example, in the linear models. And we can see there is a square term of the error between the regression and the points, the training target values. And here we have the regularizer, where we want the weights to be as small as possible. And our y is calculated by the linear combination of weights weighted by our weights plus the bias. Now we will reformulate this quadratic error function, which we have here, into we replace it with the epsilon insensitive error function, which will its profile looks like this. So here we have the standard error function, which has a certain error associated with as a parabola, and here we see that we have another error function, and this is the epsilon insensitive error function, or its plot. Now, how is the epsilon insensitive error function defined? Imagine that we have a regression, we have a certain expectation of the t with respect to a given x, and that defines as basically the mean of this distribution. And now that's basically the y of each training point. And now this difference, if this difference is somehow smaller in absolute values than a certain epsilon, then we will say that the error is 0. So we have here this definition where this difference between the target value of the training point and the estimated value, if their error is smaller than an epsilon, then the error is 0. And otherwise, if it's bigger than the epsilon, then the error will be defined as yxn minus tn in absolute values minus epsilon. So that means that it will be scaling linearly in absolute values. It will not be negative for the negative side. It will be also positive, the error, of course, but it will be offsetted by this epsilon, so that we have, although not really differentiable, but at least a continuous function, where at this point where we have minus epsilon, so where this is equal to the epsilon, then we have here in both cases 0, and then above this epsilon we would have a linearly increasing error. So this is the epsilon insensitive error function, and we can define it as an error where we perform the regularization similarly to here with our error function, and also we want to minimize the weights as we have been doing before in the context of the SVM. So because we are having this concept of margin, and we were minimizing this squared of the weights, which was before in the denominator, and we were maximizing the inverse of the weight's length, but minimizing the square of the weights. And this is together with our error term, and we have this again this parameter c, which we have associated with the error term, and that's why it's somehow the regularization is a reciprocal of c. So because if we would have it associated here, it will be 1 divided by c. So this is how we are basically putting the setup of our maximum margin approach for regression, and you can imagine it that we are defining a certain tube around this yxn. So this is a function in the n-dimensional space we are or m-dimensional space we are dealing with, and then depending on how many dimensions the x has, and then the y is would be a curve in this space, as it is a scalar, and then we have therefore here this kind of a tube around it, which is the tube has a radius of an epsilon, and it is kind of extruded along the curve defined by the y function, and or everything what is inside this tube, all the input points which are inside this tube will not be actually contributing to this support vector machines, will not be the support vectors, and everything what is outside or on the tube will be the support vectors. So therefore, we can express this again as an optimization problem with a quadratic programming again, and we introduce two slack variables. We had before already the slack variable Cn associated with the soft margin case. Now we have the Cn is bigger than 0 if the points have the target is bigger than the y-xn plus epsilon. So it's outside the tube. And we have also, so in a 2D case here, we have also the Cn is bigger than 0 for the points where the Tn is smaller than the y-xn minus epsilon. So here we have the y, and then minus epsilon is here. And if the Tn is even smaller, then this C hat n is bigger than 0. So these slack variables are equal to 0 for all points which are inside. Like here we see these various points which are inside, and the tube and defined as y-xn minus epsilon smaller than Tn, and the Tn is smaller than y-xn plus epsilon. And then from that we can define that the Tn is smaller than y-xn plus epsilon plus the slack variable. So as we had here this definition for the tube, we simply add here this the slack variable to these two, and still have this formulation where we are kind of within the tube, which is expanded by this slack variable. So with these Tn's. So that's for the points which are outside the tube, epsilon insensitive tube, and they are therefore also the support vectors. So in other words, we will be using for regression only those points which are reasonably far away from our regression line, because we want them to somehow shape the regression line to be within our within these points. So we have the one condition here for the points above the function. Then we have the points below the estimation function. So this is either or, and in either case, the slack variable is never smaller than 0. It's either 0 for points within the tube, or it is bigger than 0 for points outside the epsilon tube. So, and now what we would like to formulate the error function is that we simply want to minimize the error of the associated the epsilon the xi associated with our points. So this is to be minimized, and also our weight squared should be minimized. And with this, we are defining this maximum margin concept as defined in the case of classification. So having this, we can formulate our Lagrangian for the minimization for the primal variables. So we have here this formulation which we had before, which we want to minimize. And at the same time, we want to ensure that the Xi n and Xi hat n will be bigger than or equal to 0. So that's this constraint here, which we are maximizing. And then another constraint which we are maximizing is the formulation before. So for the points which are like outside this the tube. So we are, with this, we are maximizing the margin, and here we are also maximizing the margin on the bottom. And then, again, as we did before, we can derive out the primary variables, the W and the B, and also the slack variables, Xi n and Xi hat n. So when we do that, we end up with the partial derivative with respect to the W, and we can see that the partial derivative here will end up in the weights, and then we have this term is associated with this term here, because this y contains, of course, the weights, and therefore that's integrated out, and we are left with the feature vector times the an. The rest are only constants. And also from this term here, where we have a minus yn, we are getting also the multiplier with the an hat with the phi n feature vector. So this is the result of our derivative, and then with respect to the W, and then we can further simplify this so that we put these two sums into one sum multiplied with the feature vector, and we will see here that we have here an minus a hat n. So the minus comes because here is minus, and then here is plus, so therefore we have minus minus would then be plus, and that is equal to 0. So that means that the W is equal to this sum of the difference of a and a hat n times the phi x n. And now, if we are performing the partial derivative of the Lagrangian formula with respect to the B, we end up in the formula where we have the sum of an minus sum of an plus sum of a hat n is equal to 0. So this minus an minus a hat n is equal to 0. We can also get rid of this minus here, so it will be the sum of this term. It should be equal to 0, and we can see how we can get that here. If we perform the partial derivative with respect to the b, it only appears in these two terms because the y contains the b here and here. So here we will have this plus b times an, so it's minus. Therefore, we have here the minus an, and here we have the minus, but we have also here the minus, so minus b times minus here. We will end up in these two sums, which will lead into the result we already described. What remains to be said is about the partial derivative of the slack variables xi n and xi hat n, where we can see that they are occurring in many terms here, in basically almost all of the terms except of this weight term. So, and we can see that so from here the derivative will be simply the c. With respect to particular xi n will be just a c. From here will be just a an, and then from here it will be the mu n, and that is equal to 0. Therefore, the a n plus mu n is equal to c. And also we have for the xi hat n the similar result, where we can see how this c hat is also coming out xi hat is coming out here as a c, and then the derivative here again will lead to the minus of the mu hat n, and then here we will have the minus a hat n also, and this is equal to 0. So we have a very similar outcome for the xi hat n. So these are now our variables replacements or substitutes or constraints, such that in the dual form we will then represent our outcome in this way, in the new formulation of the Lagrangian formula, which will then be only based on the vectors a and a hat. So the a hat are, of course, the Lagrangian multipliers which are associated with the constraint which is from below, and a are the constraints which are from above. Let's have a look what all these constraints, how it turns out to be reformulating our Lagrangian, and also let's have a look at what it actually means, all these replacements. So first of all, we are not going to perform all these calculations as we have done it for the classification. For the regression, we simply take the result which is mentioned in the book, and we can see how we are approximately getting to these results, because we had this difference between a n and a hat n several times. So for example, in the weight squared, the plus 1/2 was this formula then, but minus the one double formula of this will be then resulting in minus 1/2, and then we have also the plus a n minus a hat n times tn, and then this epsilon associated term where we have the sum of a n minus a hat n is the epsilon. So with this, so is multiplied with the epsilon. So with this, we can see that there are several constraints defined based on also from the results which we have observed on the page before, that the an and the a hat n is smaller or equal than 0, and bigger than equal than 0 and smaller than equal to c. So it's again within this box as we had it before, and then c minus a n times the slack variable is equal to c minus a n times the a hat n times the c hat n is equal to 0. So that's all both constraints coming out of this KKT constraints or conditions, and then also the terms here where the an times this distance measure is equal to 0, and also from above, and this is the same formulation from below. You can see that these two formulas are very similar, except of that here is the minus yx and plus tn, and here is the opposite. So this is what we obtained from the inequality, where we said that tn is smaller or equal to this term, and then we put this tn on the other side, and then we had this term has to be bigger than 0, bigger than equal to 0, and we have a similar term formulated for the from below. However, there after we multiply it by -1, then we have changed the sign of the inequality, and therefore we were able to obtain this formulation, however, with y, x and negative plus tn. So now what, and then if we will be performing our our regression, then on a new set of points, we can see that we can utilize this formula, because this, in fact, as you might remember, was very close in the formulation to the W, where the W would be this term times the phi and in the sum, and the phi is multiplied by this by the another phi and forming as the kernel, which is the dot product between the different feature vectors, and plus b is because we have the weight times the feature vector plus b. So this formula therefore is easy to interpret why we end up with yx this way. Now, for in this case, we can hold a little, because this formulation is going through all the points which are constituting our training set. However, this is not necessary, because for many of these points, the ans will be 0, and therefore this whole term will be 0, and that therefore these points which are inside the epsilon tube do not need to be considered in the calculation of the yx, and only those where either the an or minus hat an are not equal to 0, only those will be considered in this sum, contributing to this sum, and therefore we only need to care of those and do not need to iterate over the entire set, but only over the support vectors, analogous to our case of classification. So what these KKT conditions also imply is the following. So the coefficients an can be only non-zero if the epsilon plus the xn plus y xn minus tn is equal to 0, implying that if that it either lies on the epsilon tube boundary or above the upper boundary, or analogous to the head, which is the below. So meaning that this equality can ever be satisfied for any points which are within the epsilon tube, because this value plus this value is already bigger than minus tn, and the xn is a non-negative quantity. Therefore, these two need to be bigger than the tn, and therefore it cannot be at 0. It can only be 0 if we are at least on the epsilon tube, then the xn will be 0, and if we are above the tube, then the xn will be non-zero in order to satisfy this equality. Therefore, we see that all the points which are inside the tube will have the an, and actually the a hat n also equal to the to 0. Also, it is important to mention that for each point, if an equals 0, then a hat n cannot be 0, and vice versa. This holds for the support vector points, of course. So either they must support vectors will have either one of these ans will be not equal to 0, and if one is equal to 0, then the other one cannot. So, and also support vectors lie on the boundary or outside with an not equal to 0 or a hat n not equal to 0. So this means that they cannot both be also non-zero. They can, for all points, they can be both an and a hat n can be 0. For support vectors, one of these is non-zero, but only one. And for all the points within the epsilon tube, they are both an and a hat n are 0 and can be left out from the estimation for new points. Now let's have a look how we calculate the B from the set of support vectors. So the B can be calculated analogously as we did it before, and we see that here it is calculated from the support vectors, which in fact after the optimization lie between 0, n lies between 0 and C, similarly to the A hat n. If we choose to use those for the calculation of B, in that case, when we are lying on the boundary of our margin or tube, the Cn is equal to 0, and therefore the epsilon plus the yn minus Tn is equal to 0 because we are on the boundary. So we can choose those points, or analogously we can choose the points which are at have the hat n, and here we see how we can calculate the B. So here we have simply the formula which is describing that we have the epsilon plus the yxn minus Tn is equal to 0. So this is actually this formula here, epsilon plus yxn minus t is equal to 0. And this formula here just has a slightly different formulation for our y. And now from this we can express the b with respect to both the Tn and the epsilon and the sum which was coming from the term y. So this will give us the B, and in general, we would like to use as many support vectors for the calculation of B as possible. Finally, we will again relate our attention to the new SVMs as a special form of SVMs, which is again having a slightly different formulation, where instead of explicitly defining the margin is defined in an implicit way. So we, instead of fixing the epsilon, we will be fixing the fraction of maximum points lying outside the tube to nu n. So in this case, we are having a similar Lagrangian dual form as before, except that we do not have the term with epsilon anymore. And also we have our an and a hat n goes not between 0 and c as permitted values, but 0 and c divided by n. And we have a constraint that a minus a hat n is equal to 0 as before, and that has actually removed our constraint epsilon associated with the epsilon, and then or term from the formula, and then we also have this term here, which is limiting the amount of points which can be actually considered as support vectors. So we can see that, imagine that we have the an is equal to, let's say the maximum value is equal to c divided by n, and it could be either an or a hat n. So if we have this formula and we iterate over n times, if we, in the most case, we will have one or the other will be equal to non-zero. And if we say non-zero, we will say that it will be equal to this maximal value. So we will have n times c divided by n result of this sum. So we will have, the outcome will be basically c, and this constraint tells us that it's not a c, but it's a new c. Therefore, we are limiting the amount of these support vectors to be have at least new n support vectors. So this is limiting actually the elements in the tube, in fact. And then Finally, for all these regression tasks, we have the parameters or hyperparameters like nu or c or epsilon, and either we can set them manually or we can set them also in a form that we calculate in which case does the regression function has the smallest error, and that we can define by the cross validation. So we will have just a subset of our regression points always, I mean the input data, training data, and this subset we will train, and we will see how it performs on a certain parameter settings, and then we will choose those nu and c in this case for new SVM regression, where the model is performing the best. So we will need to perform the training many times. Finally, we can see how this SVM for regression works, where we see that we have several of input points, but not all of them are contributing to the regression in the sum. Only those which are considered the support vectors, and those are now here encircled, so that you can see that only these points are basically forming us the regression curve, which is here, and those which are inside the tube are not contributing.
About the techniques called relevance vector machines, which are related to the support vector machines and are also based on sparse kernel approaches. So now let's first recapitulate the kind of the weak points of the support vector machines. The support vector output represents a decision and not a probability. So it's not a probabilistic method, and it's basically a decision function. Its multi-class version is problematic, and only the two-class classification is well formulated for the SVM technique. The hyperparameters like the nu and c, and in the case of regression also the epsilon, need to be found using cross-validation. That means that we will need to perform training several times in order to find the best hyperparameters. However, in case of the relevance vector machines, we will have several advantages which are somehow addressing problems of support vector machines, and the relevance vector machines will be a Bayesian sparse kernel technique for regression and classification. Generally, it leads to sparser models than SVMs, leading to faster performance at inference time. At the training time, it's hard to say which training performs faster. Certainly, one training of relevance vector machines will have higher computational complexity. However, when we consider support vector machines and the nature as a decision function, we will need to perform several trainings. So it's a question whether several trainings of support vector machines are faster than one training iteration of the relevance vector machines. So let's have a look at what these relevance vector machines are. Related to linear models for regression, we will start talking about the relevance vector machines for regression, and they are related to the linear models, but then they are expressed in terms of kernels, and that's why we are having them in this from this kernel perspective and from the sparse kernel perspective, as we will see. So first of all, our conditional probability in case of regression, as we know it, in case of weights and biases is given as the probability of t given a certain x and certain weights and the precision beta, which is governing the noise in our estimation process. Now, or in our output data, in fact. So, and then we have this is basically a Gaussian distribution with the mean and with the variance, where the beta inverse is the variance. And as we know, the mean here will be equal to the linear combination of weights and the feature vector. And here we follow kind of a similar strategy for the relevance vector machines, because it's an instance of a linear model that mirrors the structure of the support vector machines. So the basis functions are, however, given by kernels associated with the training set points. So we can see here the formulation for the relevance vector machine, where we have the function y, which is basically, we have here the same formula as we had before for the support vector machines, except that the an Lagrangian multiplier is now called wn, but it is more related to the an than to the weights than which we are familiar with from the linear models. So then the kernels do not need to be positive definite in the case of relevance vector machines as compared to the support vector machines. And in principle, the basis functions are not bound to the number or locations to the training data points. Are following from the linear models, and therefore we will be defining first our training set x1 to x capital N and the corresponding t1 to tn, and we will be defining first our likelihood function as we were doing it before, where our probability of the entire target outcome given the entire input and the weights and the noise precision of our target values is given as a product of these individual conditional probabilities, which we are using for expressing the probability of a given t for a particular training input, and we are performing the linear combination of the features in order to find out the mean, and then we have the variance expressed by the beta inverse, or then precision is expressed as the beta. And now this is the likelihood function, and in case we want to express a posterior of the weights, we need to define a prior, and we are defining the prior. However, here the prior for the weights is not a single scalar as we had before, where we multiplied an identity matrix with an scalar value alpha, and that was leading to an isotropic Gaussian. In this case, we have actually a different hyperparameter alpha for each weight parameter. So the alpha vector is from A1 to AM, because we will have now the M total products of our in our multivariate Gaussian distribution for the prior for the weights. So here we can see that it's a product of single variate Gaussians. For each component of the weight, we have a zero mean, and our variance is the alpha I inverse. And this prior, when multiplied with the likelihood, will be proportional to the posterior. And we know that out of this, we can formulate our posterior by simply knowing how the posterior is built from our previous discussion in the linear models section, where the posterior, which is the weights given the training set t and x, and the hyperparameters now alpha is a vector and beta is a noise precision and a single scalar value from the likelihood, we have now this is equal to, it's a normal distribution with a certain mean m and with a certain covariance matrix epsilon. Now the M is given by this formula here, and the epsilon is expressed here, and we can see that we had an earlier result of a posterior probability distribution for the weights in case of the Bayesian linear regression, and there we realized that the mean and the variance were calculated. So first the variance inverse, so the precision, was calculated as the S0 inverse plus the beta and the design matrix transpose times the design matrix. So we should see something similar for our sigma here, and our sigma is in fact the covariance matrix, while this is now still the with the powered by -1, so the inverse. This will be the precision matrix. So we need to make an inverse of this in order to get the Sn as a covariance matrix. So that's why there is an inverse, which here is not the inverse. So we can see that the second term is identical here, coming also from the beta, which is the precision of the likelihood function probability distribution, and then in this S0 inverse, which is the precision matrix of the prior, we have the precision matrix of the prior is defined as A matrix in our case, which is a diagonal matrix with these entries of alpha I, which are the precisions of each single variate normal distribution. So 1 divided by alpha I is the variance, and alpha I is the precision, and we form this way the matrix A, which is becoming here the term, and then we perform the inverse, and we have our covariance matrix sigma. Once we have the covariance matrix sigma, we can also express our mean, because we can see that the mean is calculated from the covariance matrix here of the posterior, and then we have some contribution from the prior, and then plus the likelihood contribution multiplied with this covariance matrix. Now for this first part here, we have the M0, which is the means prior mean. We have 0 prior, so this is a single variate, but in the multivariate case we will still have the 0 prior, and then therefore this first term will be removed, and we have only the second term. So this term is now multiplied with the Sn, and we can see that we have the Sn is in our case equal to the epsilon, so we are now having the mean value as the epsilon times beta and the phi transpose t, exactly as it is here, only that the order, the scalar, has been taken out as the first entry in the term. So we now know how we can calculate the posterior for the weights, which will be useful for our further treatment, and also for expressing our Bayesian formulation, which is the nature of the relevance vector machines. Express the full predictive distribution from the Bayesian treatment, we will have a look at what we do with these hyperparameters alpha and beta. And in this case, the alpha is a vector which is not a single scalar as we had before associated with the prior for the weights. This is now a vector each weight has its separate alpha precision value. And the question is, what values should we put for this alpha and beta? And the answer is that we simply can find it out by the evidence approximation, and we can use the maximum likelihood estimation of type 2 on the marginal likelihood or evidence in order to find out pointwise estimates for the vector alpha and for the beta. So if we do that, we need to first formulate the evidence, which is normally the denominator in our Bayesian formula, which is the probability of t given the x and so the input and the alpha and beta, and that is the integral over the entire likelihood and the prior, where we are integrating out the weights. So for all weights, what is the probability of t given x? So, and that can be calculated again from our previous results, where we know the results about the conditional distribution. So how do we calculate our marginal likelihood? As it is the convolution of the two quotients, where one is the quotient which determines the weights given a certain hyperparameter, and then the weights is the conditional random variable in the next probability distribution. So we were dealing with that before, where we have here, we can see that we have the probability of x and probability of y given x. So we will use exactly those formulas here, and we can see that so what is the mean? So the mean is calculated by this a times the mu. The mu in our case comes from the w, and that is 0. So no matter what the a is, this will be 0, and we have that 0 here, and then plus b. So what is the b in this case? So that will be 0, because the likelihood function doesn't have any plus term in its formulation. It's simply the weights multiplied with the feature vector, and therefore we have for the result of this convolution, the resulting mean is 0, and we need to calculate also what is the covariance matrix. And the covariance matrix, we can see it here. It's calculated based on this already very familiar formula, where we have the L inverse. The L is associated with our conditional probability, so the conditional probability, that will be the beta inverse times the identity matrix, and then we have the A lambda inverse A transpose, and the A is in our case the design matrix, because that is multiplying the weights in this linear model. So that would be the X will be the weights, and the A will be the design matrix. So that's why the design matrix is the A. And then we have the diagonal matrix, which we have defined before, which is defining us this matrix of the covariance matrix of the prior, and then we have the design matrix transpose. So we have now defined the evidence or the marginal likelihood, and then we will simply perform the maximum likelihood estimation of this probability distribution in order to find out what will be the maximal values, maximizing this probability distribution for given alpha and beta. So when we are maximizing it, we are performing the logarithm. The logarithm will have this outcome, because we have here these normalizing terms, and then we have the exponential term here. And when we perform this type 2 maximum likelihood estimation for re-estimation equations, we come up with a certain gamma measure, which measures how well is the weight determined by the data. And then this gamma is an input for calculating our alpha components, and also for the beta. This, we will not go into details how we exactly calculate these. We will simply say that they are very analogous. We can see that gamma divided by this dot product here is very similar to this, term for the alpha I, and the beta is, or beta inverse, is also very similar in formulation. And for the gamma, we might see that there is a slightly different formulation, but we will simply leave the gamma calculation to the point that we define it here and use it. Now, if we want to find out the alpha and beta, we will need to do it as we had to do it before, also in an iterative fashion, where we are forming the m and the sigma as the quantities for our posterior, and then we are using these values for calculating our gamma and for calculating the out of it the alpha and beta. And then again, once we have calculated the alpha and beta, we again calculate what are our mean and sigma values, and we perform several iterations of this process until we converge to a stable representation both of the mean and the variance, and also the associated hyperparameters. And with that we maximize the model evidence, and with that we will also have the hyperparameters estimated which fit the data, our data, the best. Once we have these alpha and beta, which seems like a regular process which we have been doing before, the difference is that the alpha is not a single scalar, but it is associated with every weight which we have been dealing with, and that is very important to keep here in mind. And the reason is that if the alpha will be going to a very high value, and then the associated, so this is then the associated weight will have its probability distribution as a single variate normal distribution will be with mean 0 as always, but its standard deviation will also be becoming 0. So the weight will be becoming insignificant and will not be really contributing to our model. So we will see that in a moment. So so the hyperparameter alpha I in some cases is driven to a very large values, which conceptually will lead to infinity, and then the corresponding weights wi will be nearing the normal distribution 0, 0. And at that point we can say that both the weight but also our feature vector in the basis function in our basis function vector is playing no role in making predictions and is removed from the model. So we remove the entire entry of this feature calculation from the model because it's not expressing our data well, and it's not contributing to the predictions in any way. Then we will take the remaining non-zero weights, and those will be called our relevance vectors, which are in fact determined through the automatic relevance determination, which we have been discussing recently in the case of the kernel methods. So as you can see, we have been here dealing with every entry of the weights and then associated feature, and that really was identical to the automatic relevance determination process, and through this process we have obtained the relevance vectors. And the relevance vectors will generally be much fewer vectors or input points than we have been dealing with in the case of support vector machines. Now, what remains is to express the predictive distribution of our new t given x and the training set capital X and t and our tuned or predicted pointwise estimated hyperparameters alpha as a vector star and the beta as a precision noise precision. And that is equal to, as we know, already to the product of the conditional probability of new input vector x of given new vector x of t with our any weights actually, which are weighted by the probability distribution by the posterior of the weights. And here we are integrating out the weights effectively. So we consider all the weights in this predictive distribution and integrate them according to their respective probability. We know that that can be again realized as a convolution of two Gaussians, and we can again use our formula which we had before and as on the previous slide, in fact, and we can see that here we have the posterior now in this case, and this weight is a linear is a linearly transformed as a mean for this probability distribution. So out of that, we will lead to the fact that this mean is m, and the mean is multiplied with the feature vector because that is the a, and plus b, the b is 0. Here there is no additional plus b, and then we have as the so that is the mean, and basically calculated like this, and then we have this formula here where we are calculating the L inverse is the beta inverse, and then we have the plus the, so this is we are having actually a single variate normal distribution out of this because this is a single variate outcome. So therefore this sigma is having this beta inverse here, the tuned or the estimated beta inverse as the variance, and then we have the variance associated with the A, which is the phi X transpose, and then we have L inverse, which is the capital sigma, and then we have the A transpose. So with this, we have calculated our predictive distribution, our sigma, and also our mean, and we can predict what will be the given t of for the new input vector. And the advantage here is that in this case, we in fact do not need to deal with all the inputs, but only those which for which the features are considered as relevant. Now these relevance vector machines, which on one hand look like a linear regression, but on the other hand, in case we are dealing with, for example, the Gaussian kernels have the structure of the support vector machines, can be devised in such a way that we are eliminating by this the ARD approach, meaning the automatic relevance determination. We are determining by that the alpha vector, and this alpha vector is associated again with the weights. These weights are associated with a various phi functions, so the basis functions, and these basis functions are eliminated. Therefore, in our final representation of our matrix, like the matrix capital phi, which is the design matrix, which happens to be also the kernel matrix, the K, or gram matrix for that matter, that will lead to the fact that these matrices will become smaller because we will be eliminating the basis functions, and by eliminating these basis functions, we will be essentially reducing their size and their complexity. And this means that all the basis functions which are not contributing to this to the prediction or to the estimation will be eliminated, and we will be left out with only few basis functions, and there, in case of Gaussian kernels, their associated center points, like we have it, for example, here, which will be then determining the having the predictive distribution will be governed by these. So here you can see we have the same example as we have seen for the support vector machines. Previously, there were several points which were the support vectors. Now we have only 3 relevance vectors which were remained. All the other ones are not substantially contributing to the estimation, and therefore they have been eliminated. So we are ending up with a very compact representation for our prediction of a t given a certain new input point x. It needs to be mentioned that these basis functions, localized basis functions, like for example the Gaussians, their predictive variance for the linear regression models become small in regions of input space where there are no basis functions. Meaning, like for example, here I would not have now basis functions, but the variance is not increasing here, is small. And that is actually the disadvantage of the relevance vector machines, which is kind of inherited from the Bayesian linear regression. So that can be alleviated with the Gaussian processes which do not suffer from this problem, but otherwise they are much more computationally costly. So generally we can say that the number of relevance vectors is significantly smaller, even order of magnitude smaller, than the amount of support vectors. And however, training of relevance vector machines involves non-complex function. We have seen that when we are estimating the alpha vector, there we have in fact non-convex representation is manifested through the fact that we have to iteratively re-estimate these hyperparameters, and in order to maximize the marginal likelihood, and therefore, as this is non-convex function, generally requires and m times m matrix inversion, so the computational complexity is O of m cubic compared to the support vector machines, which generally have the quadratic computational complexity. So this is, on one hand, during the training, is the relevance vector machines might be more computationally complex or costly. However, it is also needs to be said that in the relevance vector machines we are determining the alpha vector star and the beta star through the automatic relevance determination as a single training run, while the support vector machines need to run cross-validation, and therefore multiple training runs need to be established for determining the parameter c or epsilon or the parameter nu. So therefore it is not straightforward to say that our relevance vector machines would be in the training time more computationally costly, because the fact that we need to perform cross-validation can actually also lead to extensive training times. We can say, however, that the relevance vector machines have the advantage that they are faster in the inference time and less because they are dealing with less complex models, and also well, it's a model which is a probabilistic model, unlike in the case of the SVMs, which are not really probabilistic approaches, and they are simply a decision functions. So with this, we will continue and discuss the aspect of the analysis of the sparsity of relevance vector machines.
We understand the concept of relevance vector machines and how we in principle can calculate the vector alpha, we will delve more deeper into the analysis of sparsity of these Bayesian linear models. And at the end, we will also devise a new way of calculating the alphas, which is much more efficient than the previously introduced method. We will help ourselves with an illustration on a small data set which has just 2 points and 2 observations, where we have the target values t, which is the vector t1, t2, and a single basis functions phi of x, where the vector of phi is the phi of point x1, input point x1, and phi of input point x2. And please note that these are, therefore, if we would be looking at the design matrix, these are the columns. So in fact, we are, when we are reducing our model, we are essentially removing columns from our design matrix. For each column, we have one basis function. So, and if the basis function doesn't really contribute sufficiently to the model, it will be pruned. And now we will see how does actually this look like, and geometrically. And then also we have the parameters alpha and beta with marginal likelihood in our simple example, where the marginal likelihood or the model evidence is this normal distribution, zero mean, and with the covariance matrix C, which we have already discussed is having the component from the noise and then the component associated with our basis functions. And now we have only one hyperparameter alpha, not the vector, because we have only one of these basis functions. So, and we can see now that if we are now first having our covariance matrix just governed by this beta inverse, by this precision, we will see that our distribution, normal distribution of the model evidence is simply an isotropic Gaussian, and in this multivariate setting or two-dimensional setting, and in fact it is not really giving us to very well predictive power for estimating the t at this point. However, we can add our basis function, and the basis function, imagine that we simply perform the transformation of the x1 and x2 in this two-dimensional space spanned by the t1 and t2 axis, where the t is here, so this is our target vector in this linear space, and now we will be plotting the vector which is associated with the transformed input points, the vector phi, which has the x1 and x2 as an inputs, and these two coordinates are therefore spanning this vector. And now we know that in our linear models, we use a linear combination of these type of vectors weighted by the weights W in order to find an estimate for the target outcome t. Now we can see that from the origin, the direction towards t is this vector, and the vector phi is, if not completely orthogonal, it's quite orthogonal to this direction. So we can see, in fact, that it doesn't really contribute. So if we want to add up several vectors so that we end up somewhere at the point t, this vector phi will not really help us there because it doesn't point to this direction at all. So this vector will be in some sense useless for the prediction, and therefore it could be pruned. So that is the geometrical illustration of what is going on. And if it is not pruned, then our matrix our covariance matrix is actually getting this elliptical shape, and it in fact distributes more density towards the direction where we definitely do not have any of our t values. So it is actually somehow wasting the probability distribution in directions where none of our output values are really located. So ideally, we want all these vectors which will be elongating our ellipse towards the direction of the t. And those will be valuable vectors, and those which are orthogonal to it are more useless. So also it is worth mentioning that this model evidence is actually a zero mean Gaussian process. And we have already mentioned that if it points away from t, it contributes little to nothing to the overall linear combination. And then the associate alpha would elongate the distribution in the direction away from the data. And for basis vectors which are phi to phi m, if we have m basis vectors, if the vector is poorly aligned with t, it should be pruned from the model. That's the concept of these relevance vector machines. And now let's have a look how this can be pruned from the model. We will now present a framework how we can calculate the alphas in order to find out whether a certain feature vector or basis function should be included in the model or not. So we can imagine that with our previous definition of how we were calculating our alphas, the hyperparameters alpha require re-estimation in implicit solution, where on both sides of equation we in fact have this alpha, because the gamma is also including the alpha in its definition, and therefore we need to perform this re-estimation. And in fact, during the re-estimation of alpha j, alpha I, all other alpha j's need to be fixed. So this is a complex process, and for each basis function, we will need to perform this re-estimation separately, which will not be very computational efficient, or it will be quite computationally demanding. So instead, we can think of a slightly different formulation by expressing the alpha I directly from the marginal likelihood and determine its stationary point explicitly. So let's have a look how we can obtain this. So imagine that we have our covariance matrix C, and this covariance matrix is built from these basis vectors. And these basis vectors, it is built in the following way. So here we have the noise component of the variance, and here we would have the part of our covariance matrix, one component associated with one basis vector or basis function, and also it is weighted with the alpha j inverse, which is the variance in that direction of that basis function. Now we are performing a sum. Therefore, we are calculating sum of all of these basis functions, and that is forming us this covariance matrix as we have seen it before. And now, actually, we are going for j through j equals 1 to m, but not including the I. So the I is taken out separately from the sum, and we can therefore express that our C is equal like the covariance matrix C minus I plus the component, the ith component of the basis function, further weighted by the variance alpha I. And now that we have it, we have separated out this ith contribution and can study what is the covariance matrix of this C minus I. And in more detail, we will actually compare the Lagrangian of this our model evidence, and we will see, because maximizing the model evidence was previously the way how we were maximizing our alpha and beta hyperparameters, so we will get to maximizing the model evidence or comparing the two different model evidences. We will come to that. Just before that, we need to express ourselves some variables or some quantities, like for example the determinant of C is equal to the determinant of what we have just defined here. So is the C minus I plus alpha I inverse phi I transpose determinant, and that is equal to something which we can see here as a general rule for matrices, where the result of this kind of formula is equal to the determinant of A times this, and we will see that it corresponds to our formula as we have it here, just with different naming convention, if you like. So here is the C minus I times the 1 plus alpha inverse, so that is actually part of each of these two vectors, where the v and u can be the same in this case. So, and the C minus I is our alpha, therefore here it is inverse, and then we have the phi here for the u. And that is our reformulation of determinant of C, and we can see that the determinant of C we can express through the determinant of C minus 1. And then, furthermore, we want to express the C inverse as an expression of the C inverse C minus I inverse, and that is equal to, according to this formula here, it is equal to the C minus C inverse is C minus I inverse minus, and then we have the B here, which will be this CI, and then we have the U and V, and again CI, and the similar situation we have here, except that we are also adding here alpha inverse in the numerator, because that is associated with either both of these vectors or one of these vectors, because it's a scalar which can be scaling one of these vectors, either u or v, as desired, or both. And then we have a similar term here, where based on this knowledge of this matrix algebra, we can express the C inverse through the C minus I inverse. So finally, we have compactified this representation also so that it is identical with the one in the book. And now we can use these two quantities where we express the C associated quantities through C minus I associated quantities to see what is the difference between these two in terms of marginal likelihoods or their Lagrangians, so log marginal likelihoods. So a negative log evidence without constants, meaning without the ln 2 pi, can be expressed in this way, and also this minus has been removed for simplicity, and we see that we have a component of ln and with the determinant c, and then we have the part from the exponent where we have t transpose c inverse t, and that can be, after our calculation from the previous slide, replaced. So this quantity can be replaced by this quantity because c is multiplied, or c minus I is multiplied by this quantity. Therefore, we can see it as a two logarithms addition, and then plus this quantity here is the ln of this quantity, but expressed through the C minus I. And we knew that it was C minus I inverse, and then this complex numerator and denominator. And what we have also done right away was that we multiplied it from both sides of these expressions with the T transpose T. And now we have the formulation where we see that the Lagrangian of alpha of the full model of C is actually expressed by the C minus I, and therefore that makes our job easier to find out what is the difference between the Lagrangian alpha and the Lagrangian alpha minus I, meaning that the log marginal likelihood, which is not including the ith basis function. And this difference can be simply expressed because the marginal likelihood or evidence of and the logarithm is simply ln c minus I, so has a very similar structure. Instead of c, there is c minus I. So we can put these two into a subtraction where we collect together the terms associated with the discriminant and also determinant, and also the terms which are associated with the exponent, or were associated with the exponent before the logarithm operation. And we can see that this difference, in fact, here is, so if we perform this minus this, it's like this ln c is expressed here. So, and we already have the ln c minus I here. So if we subtract this, this is the difference. So, we can also express it. We can now replace this complicated structure here of this squared of the basis function with a quantity, because it will be a scalar at the end, with a quantity called Si, and which we will call sparsity just in a moment. So that is equal to this term. So our ln is 1 plus alpha I inverse Si. And then for the other part, this exponent, previously in the exponent of the exponential function, we have this subtraction from these two terms, and that also we know what is it equal to, because we are again expressing the square term of t for the matrix C through the matrix C minus I. So if we subtract this away, this will be the residual. And what is the then the meaning of this? So first of all, let's we can again tidy it up a little bit by expressing this another quantity, which is called qi, and that quantity is calculated as the product of the vector times the row vector times the matrix, and then times the vector t, and that is the quality quantity, and we will soon express what it actually means, also the sparsity. So we have here a simplified formulation of this term, and we can see that now the difference between two Lagrangians, which are really the log of model evidence, and model evidence is somehow capturing the quality of the model in terms of complexity versus expressivity, and we make a difference here between. So basically, it's a difference of quality between the two models, and this difference so expresses basically what happens if we add this basis function to the model. How much will we see some improvement? And we can see that that is basically expressed here, and we can call it now a lambda function of a alpha I, because that's the alpha I associated basis function which we will be which we would be adding to the model, or subtracting it from the model. So here we have the expression which we have obtained already here. So this last term basically stays the same, except that we have this first term is a logarithm, and we can replace this formulation here with a fraction where we have the alpha I is on the like, if we will express this as this one as alpha I plus si, then we will have the alpha I si, and then we will have the one for alpha I si, and then we will have the alpha I inverse si, and by certain operations we will land to this expression here, which further can be expressed as lambda I, alpha I minus logarithm of alpha I minus logarithm of alpha I plus si. So this is the formulation which is identical to the one which is in the book, which we wanted to end up with. We will now use this function, this kind of a residual of the after adding the one basis function to the model evidence and then expressed in this Lagrangian. We will now see more in detail what these quantities then represent. So we have introduced the quantity Si and Qi, and we named them. Si is the sparsity, and the Qi is the quality of the basis function phi I. So the sparsity measures extent to which the phi I overlaps with other basis vectors. So that is how much redundant is this basis function, and the quality measures the alignment of the phi I with the error between t and y minus I, so predictions without the phi I, meaning like we have a certain difference between the target and the predictions without that basis function, and then we are seeing how much is this qi, how is the phi I by this quantity how is expressed how much is the phi I aligned with this error, with this vector between these two, between the true values and the or noisy values and the phi and the y I minus 1. So and we will be basically attempting to maximize the contribution of this basis function, and we will see if we maximize it, what is the value of this maximization in terms of the alpha. So what we can do here, we have our lambda function, we can perform the derivative, and this is a relatively simple derivative to perform. So we have here the ln alpha I, and then another logarithm, and then some fraction. So simply the result of this logarithm are these three terms, which we can further simplify or put together in such a way that we express these two. This is 1 divided by alpha I, 1 divided by alpha I plus Si. We can express it together, and we will have Si here. So this is putting these two terms together. Then if we are multiplying it on both sides with the numerator and denominator with the alpha I plus Si, then we will have here a square term, and here we will have a slightly more complicated term, but we are getting closer to the denominator here for this Qi, and now we can put it all into just one onto one fraction, and that is the result of our derivative, and then we set it to 0. So we want to maximize it, and that's why we perform this derivative. Based on this, if we just take away this denominator, because it cannot be 0, then just the numerator can be used for solving the alpha I. So here we have the numerator that is equal to 0, and then we are putting one part on the other side, and then we are putting the Si into the denominator, and then we are inverting this whole thing so that we get an expression for alpha I. So we have now actually solved an explicit definition of what the alpha I is in order to maximize this difference between the model without the basis function and with the basis function included. Now we can analyze this alpha I and also the corresponding quality and sparsity values, and we come to the following conclusions. So if the alpha I is bigger than 0 and the Qi is bigger than the Si, then in fact we will have the following kind of a function here, which is the function of the lambda, and so that basically is if our Qi squared term is bigger than Si, then our function profile will look like this. It will have a one unique maximum for a finite alpha. And so this on the horizontal axis, we will have a logarithm of alpha, by the way. And then if our alpha I is bigger than 0, but we do not have the Qi squared bigger than Si, but the opposite, then we will see that alpha I will tend to be the biggest lambda will be for alpha I in the infinity, and this suggests pruning. So if the quality squared is smaller than the sparsity, then this is an basis function which is not expressing our, it's not contributing to our model substantially. So finally, we can recapitulate that this can be organized into an algorithm for sparse Bayesian learning using these relevance vector machines, where we first initialize the beta, and then we take one of the basis functions and calculate our alpha for this basis function, and also the all other alpha j's are infinity because all other basis functions are excluded. And then we can gradually include more and more of the basis functions such that they are contributing to the model incrementally more and more. And so we will evaluate our posterior probability for the weights, and then out of that the SI and QI for all basis functions, and then we will see select some candidate basis function, and if for that the QI squared is bigger than SI and the alpha I is infinity because we set it in the beginning, then we add this to the model, so one which is particularly suitable. If we have calculated these quantities for all our basis functions, and this basis function is already included in the model, we simply update the alpha I with these new quantities. And if we realize that these two quantities are in inequality in the opposite direction, namely that QI squared is smaller than the sparsity, then we remove these phi I from the model and set the alpha I to infinity. And if such a case is already in a removed model or not yet included model, we will simply not add it again. And then we update beta and we go back to select candidate. In this way, we incrementally grow our model with basis functions which are strongest contributor to the model and are useful for estimating our values for in the regression task. So this is all for the relevance vector machines in the context of regression. We will just now in the next look into the last part, which is the relevance vector machines for classification.
So vector machines can be also applied to classification. Let's revise how the linear models for classifications were defined. Similarly to the regression, we had some feature space defined by our feature basis functions, and also then the feature points after the transforming the input points to this feature space, and we formed a linear combination with the weights which served as a combination of these vectors. Now the sigmoid was basically mapping this real function onto the interval between 0 and 1 for the two-class classification. So we will be also dealing here with the two-class classification for the illustration how the relevance vector machines can be applied in the context of classification. Again, we will be employing this automatic relevance determination in this case as well, and it will be to some degree similar to the regression, except that there will be natural complications arising with the fact that we cannot analytically express certain nonlinearities coming from the sigmoid. So here we will define the automatic relevance determination prior in a way where we have our weight prior, which is governed by a vector of alphas instead of just one alpha characterizing the spread of our weights in this m-dimensional space. And we can see that it follows a multivariate Gaussian, which can be decomposed into which is a product of single variate Gaussians, where each has a zero mean, but each has a different variance or alpha I precisions. As there is no analytical integration of the integral necessary for the model evidence, we will apply the Laplace approximation to approximate this probability distribution actually of the posterior probability for the weights. So with that, we will formulate how we approximate the posterior, and then from that, this will lead to approximate marginal likelihood. So, and then we will be maximizing the marginal likelihood, which will lead to the alphas which we are interested in, and those alphas which will be growing to large proportions will be those which will be indicating the weights or the features which are not really very relevant for the estimation task based on the training set. So we can express the log of our posterior probability distribution of the weights based on the Bayesian as the product of the probability of the likelihood and then the probability of the prior, and therefore here we have also our model evidence or our marginal likelihood expressed, which would be in the denominator. But we can see that if we are interested in approximating the posterior by the Gaussian, this will actually fall out because we will now be performing the derivative of the log likelihood, the log of the posterior with respect to weights, and as there are no weights in the marginal likelihood or the evidence, this term will be therefore not present in the derivatives. So we have here therefore this formula which is containing only those terms which are containing our weights. Here the weights are contained in the y's, of course in this type of cross entropy expression. And then from the prior here, we will see that we have the weights coming from the exponent, and the rest will be the constants coming also from the marginal likelihood terms, which we will then in the gradient they will turn to 0. So if we are performing the first order derivative of this log posterior, the outcome will be, as we could see partially here, that it is this term will turn into this term, and then our term associated with the cross entropy part will turn into this design matrix transpose T minus Y, as we have seen it in the previous cases, also in the case of classification. So these are the aspects we should be already quite familiar with, and then the second order derivative will be a second order derivative of this term here with respect to the weights, and we will end up in the terms which are appearing here. So we have the design matrix transpose B, design matrix plus A, and we can, if we will look back into the linear models for classification, we will see that the gradient of the error with respect to the weights will be formulated by this form, which we have nearly the same one, except that maybe in this particular formulation in the book, the T is the first and Y is the second, which has a certain consequences on the sign. And then we have the other part associated with the matrix of the characterizing the the variance of our prior is the second term. So that is not present here because we didn't have that before. However, we have here again also the second order derivative, which we can see is this formulation here, which is similar to what we have obtained. And then the difference is that here we have some B and here we have some R, but in fact this book of Bishop is referring to this diagonal matrix of sigmoid derivatives in various letters. Sometimes it is B, sometimes it is R, sometimes it is W, and actually this matrix is always the same. It's just the diagonal of the derivatives of the sigmoid function, which will be here in this case denoted as B in this part of the book, and we can see that it is the formulation here. So once again, we will perform the iterative reweighted least squares, and for that we will have necessary. And why do we perform it? Because we want to find the maximum a posteriori estimation for the W, for the weights. What is the most likely posterior weight vector? What is our mode in case of our Laplacian approximation when we approximate with the multivariate Gaussian? So we therefore, in order to get to the Laplace approximation, we need simply the mode, and we need the covariance matrix. The covariance matrix turns out to be our second order derivative, which will be this matrix here. However, that will be only once we find the mode W, and then the Hessian at that location will be evaluated. So we will need to perform this iterative reweighted least squares, several iterations until we converge, and we converge with this gradient and this Hessian matrix being used in this iterative reweighted least squares. More precisely, we will take the characteristics of this formula for the gradient, where the gradient is equal to 0, and from that it turns out, so for the Laplace approximation, that our W star is equal to this formula here coming from the formula for the gradient, and the covariance matrix will turn out to be the Hessian matrix, which we have here, just the minus of it and inverse, because we are in fact having, by the Hessian matrix, we are calculating the precision matrix instead of the covariance matrix. So once we obtain the W star, the posterior estimation, and the covariance matrix, we have our posterior probability for the weights given a certain t and some initial alpha. Our posterior probability distribution for the weights, we can express our marginal likelihood. As we know, the marginal likelihood is in fact the product of our likelihood and the prior, and it's an integral over all possible weights. So the weights are integrated out, and therefore it's a marginal likelihood. However, we know that in fact this in this formula, if we look at what we learned about the marginal likelihood and the Laplace approximation, we can see that our marginal likelihood Z here from the previous chapter on linear classification, we can see that this function Z dz, so function of W dW in our case, is approximately equal to the functional value at Z0 and then the scaling factors, certain scaling factors which we have already devised before. And these scaling factors, we can see that there is an, previously we had maybe here it was the precision, and it was 1 divided by the precision and then square root of 2, which can be also reformulated into not the precision but the covariance matrix and then square root of the determinant of the covariance matrix. So a slight different formulation which appears. Now here we can see how we can basically solve this derivative, and for that we are using our for the Z0 we are in fact using the most likely W as a posterior probability mean, which will therefore these both terms as a product will serve as this f of Z0. So once we have solved this integral and we have approximated our marginal likelihood by this likelihood at the particular weights at the mode and the probability distribution of the weights of the mode given the hyperparameters, then we can express this product into again a maximum likelihood estimation of the marginal likelihood through the performing the logarithm, where we will have here the logarithm of the first term, of the second term, the third term, and the fourth term. Of course, now we are interested again to perform the derivatives, the partial derivatives, however, not with respect to the weights, but with respect to the alphas, the hyperparameters, as the type 2 maximum likelihood estimation. And therefore, here we have the partial derivative of alpha components of all our terms, and we will see that some of our terms will be disappearing again, like for example this constant term, or for example also the likelihood or logarithm of the likelihood doesn't really contain the alphas anymore, and therefore this term will also disappear. So we will have therefore the partial derivative of alpha with respect to the prior given a fixed weight, and then we have also the partial derivative of our ln of covariance matrix determinant. Now this is a normal distribution, and therefore from the normal distribution we will be obtaining the exponent. So this is a normal distribution, but with respect to the particular alpha I, this is the only part of the multivariate Gaussian which is non-constant. And that's the part of the exponent where we can see that our otherwise multivariate Gaussian distribution will have the alpha as a matrix A, and this matrix A is then from has the weights is multiplied with the weights from both sides, or the weights and minus the mean of the weights, which is the zero mean. And therefore, but in this case we have only a scalars, because we have all the other terms are constant. So and they will turn to 0. And therefore here we have this non-constant term, and for for the derivative of the covariance matrix, again, the covariance matrix consists of various terms, but actually the alpha is only contained in the A term, which as the covariance matrix was like the design matrix transpose times B times design matrix plus A, the whole inverse. So now we will have therefore this diagonal of alpha being the only part which is non-constant from the covariance matrix. And after we perform the derivative of these terms, we end up, and also the derivative of the covariance matrix here again with respect to alpha I, which is coming not from the prior, but it is coming from this term, which was from the approximation, this scaling factor here. So now we have the result of our derivatives is that here we have this term because the alpha simply was derived out, and in this case we have a similar situation where if we have a diagonal matrix, its actual determinant is the product of all the terms in the diagonal matrix, and if you have such a product and you perform the first ln of this whole thing, so then you will have the 1 divided by the product, and then times the derivative inside, which is the product where everything is basically the alpha I is multiplied with all the other alphas, and those will be in the numerator. So after we perform this chain or this complex derivative, then we will end up with the 1 divided by alpha I as a result of this derivative, and with the 1/2 in the front. And then finally this term will we will have the derivative of the ln, the covariance matrix here, which is which turns out to be minus ith element of the covariance matrix, and it without going too much into details, that can be obtained by this formula here, where we have this the derivative of this ln covariance matrix is a trace of the inverse times the derivative of the covariance matrix with respect to alpha I, and that results into minus ii. So that we have here as the result. And if we set it to 0, then because of we are trying to find the maximum of this logarithm, then, and also if we set this gamma I to be 1 minus alpha I sigma ii, then in this formulation which we have here, so we have this formulation here, but then we just multiplied this alpha I with the whole equation, so we end up with alpha I here and here. Then this term, this is the gamma, and we can put the gamma on the other side, and then divide by the square of the weights, and then we obtain our formula for gamma for each component of alpha. So with this we have shown that exactly the same formulation for the hyperparameter alpha can be used, or vector can be used for each of the component in order to iteratively calculate the gamma and then the alpha, and from that see how the hyperparameter is evolving and whether or not do we want to prune that particular feature from our model or not. Another approach can be also that we will approximate our likelihood function here, this one, with with a formulation with an effective target t hat. So our target t is replaced by this linear transformation, if you like, of the t, or linear approximation, to better to say, of the t hat. So with here we can see how does the t behave close to the maximum, so the mode of weights, maximum posterior likelihood. Here we are calculating the function y at this location, and then we have the first order derivative represented by this function b, which is the sigmoids along the diagonal, times the difference between the t vector and the y vector, calculated basically in this way. So if we have that, then we can see that this type of formula for the random variable t hat can be expressed in such a way that the likelihood function can be approximated by this effective likelihood, and that as it has this formulation, we can see that it has in fact the mean is this phi times the weight, and the covariance matrix is the matrix P inverse. So our likelihood now can be also seen as the normal distribution, and if we have a normal distribution of our likelihood, and we have normal distribution of our prior, in such a case we can perform again we can integrate this, and the integration is simply, as we had many times before, is simply the where we take the mean multiplied with the, so because here we see we have the random variable w, and here we have a linearly transformed random variable. So this is like a x plus b, so the a will be the phi, and the a times mu plus b is therefore the mean here. So it is still, as the mean is 0, it this phi times the 0 will still be 0, and b is 0. So this is our mean in this marginal likelihood approximation of when we, instead of the likelihood function, we approximate it by the effective likelihood function. And then also the C, the new covariance matrix, is then based on our formula, which I don't have written here, but you have seen it many times, and it's like an L inverse and then A capital lambda A transpose. So then we have it similarly here, where the B is coming from here. So this is the L transpose, L inverse, and then the phi is the A, and then this is the lambda inverse, and then this is the A transpose. So we have again formulated this marginal likelihood function, which is a function of these hyperparameters, but not of the W anymore, as the zero mean and with the covariance matrix. And then which again has the form like of this prior for the t without actually seeing the t, and then if we perform the ln of this marginal likelihood, we end up with these terms, obviously, because it's a normal distribution, and these terms have been in the beginning our previous approach, where we have calculated this relevance, this hyperparameter alpha in an closed form coming from this equation, where through this analysis of sparsity. So we had this analysis of sparsity in the previous case of regression, and here we can see that we can land at a at the same formulation of the analysis of sparsity if we perform this approximation with the effective likelihood with this normal distribution here. And once we have this formulation, we could proceed with the same steps in order to calculate the hyperparameters alpha using this approach of analysis of sparsity. So with that, we will be able also to find out which of our associated features are having alphas or weights which are having the alphas which are going to a very large number, and then the corresponding features can be pruned out from the model. The multi-class classification scenario will be not covered here, but it's in principle analogous how to prune it to the case of how we saw the analogy between two-class classification and multi-class classification in the case of linear models. And finally, you can see the outcome of these relevance vector machines, where the individual points here and circled in green are showing which points remained to these points associated with a particular feature. So we will have like a radial basis function type of kernel, and this many of them will be pruned out, and we will end up with a sparse representation, which is performing a very good job in terms of classification of these two classes here. But we can see that the individual points are much less. And also what we can see is that they are not like we have seen it previously in the case of our support vector machines. They will be kind of surrounding our decision boundary. In this case, we see that there are many points from these relevance vector machines which are actually not close to the decision boundary, but are considered to be relevant basis functions for performing the classification task. With this, we have completed the content on the sparse kernel machines. We have discussed first the support vector machines, which were decision functions, and then we have covered the second category of relevance vector machines, which are probabilistic approaches and can be seen as the extension of linear models into the direction of kernel methods, in which case we are employing the automatic relevance determination framework to find out which of our features are relevant and which are not, and those which are not we will prune out. On sparse kernel machines, and the next chapter will be